Alright, so now we're going to look at some strategies for determining extrema when we do not have a closed interval and when we're only looking for local extrema. Now, a little review for us here from pre-calculus, that if a graph exists on an interval, it has to be doing one of three things: increasing, decreasing, or staying constant. So that's fairly straightforward. We want to interpret information about a function by analyzing information about its derivative. And so if you recall that we've been kind of mentioning this all along, is that the derivative is going to tell us the slope of the curve. The slope of the curve is going to tell us what the curve is doing, going up or down or staying the same. When the slope of a tangent line is positive, then we know that the curve is going to be rising or increasing. If we know that the slope of the curve is negative, then we know that the curve is going to be decreasing. And if we know the slope of the curve is 0 for all the x values that are there, then it's going to be constant. So, and again, this was our pre-calc definition right here. All the y values at x1 were smaller than the y values at x2. F was increasing. Our calculus definition is going to be, hey, the slopes are going to be positive there. When the function is decreasing, your pre-calc definition is going to be the y value at x1 is bigger than the y value at x2. Your calculus is going to be the slope of the tangent line is going to be negative. For a constant section, we would say that the y value at x1 and the y value at x2 are the same. And of course, I'm saying this is for all x in the interval a to b. Right? We're picking x1 and x2. So for all x values in the interval, f of the first x is smaller than f of the second x. And if they're the same, then it's constant, and there we have our derivative is 0. So we pretty much already knew that. We've been talking about that all along. So we can run a test for determining where the function is increasing or decreasing by looking at, now we're specifically only looking at continuous functions again. If it's a discontinuous function, we're going to have to think about some additional things. We're looking right now if we have a continuous function on a closed interval, okay, differentiable on the open interval, then what we know is that if the derivative is positive for the entire interval, every value in the interval, open interval a to b, then it must be increasing. If the derivative is negative, then it's decreasing, and if the derivative is 0, then it must be constant on that interval. Okay? If the derivative is positive on an interval, we call it monotonic increasing on that interval, monotonic decreasing, and then constant, which is the boring one. So that's all a review of things that we already know. So if we were in pre-calculus, I could give you the graph of a function and then have you list the open intervals over which the function is increasing, decreasing, or constant. And you would say f increases for x in the interval from -3 to 1. Okay. F is constant for x in the interval of 1 to 3. And then f decreases for all x in the interval from 3 to 5. Okay. Now notice we're not even going to get into the bracket or parentheses option. They are always going to ask you for the open intervals for which the function is increasing, decreasing, or constant, and you are simply going to list them with parentheses. Now, at what values can the graph of a function change from increasing to decreasing status? Right, now I'm going to underline a continuous function can only change its status at a critical value. Okay? A continuous function can only change its increasing, decreasing status at a critical value. So this would be a value where f of c exists and it's continuous at x equal to c. And what you're looking for after we meet the continuity is that either the derivative is 0 or the derivative is undefined. And these undefineds are going to be the cases where this is your nice hill or valley, and then your undefined derivative is going to be a cusp, like this, increase to decrease. All right, now the graph of a continuous function, or the graph of a discontinuous function, now we want to talk about that separately. Okay, you can also change increasing to decreasing status at a critical point or a discontinuity, because your function can, on one side of the discontinuity, can be increasing, on the other side can be decreasing. So when we are doing our kind of sign charts for this, which is basically what we're going to do, on our sign chart, you're going to list all critical values and all discontinuities, because on f of x, because at those values the derivative will not exist, f prime of x will be undefined there as well, but for a different reason than what we had up here. Here they're going to be undefined because they're simply not going to be points on the original function. It's not going to be continuous there, so it would be discontinuous there. All right, so for example 2 right here, we have the graph of a function defined for all x not equal to negative 5 and 5. So it has our nice little discontinuities at 5 and negative 5 in the domain negative infinity to negative 5, negative 5 to 5, and then 5 to infinity. And we want to list the open intervals over which the ants walk uphill or downhill. Again, we're still not doing calculus, we're still pre-calculus at this point. As we scan left to right, as the ant walks, this ant's going uphill, so f increases for negative infinity to negative 5. Now, above I said x element of. A lot of times we drop that. We just always assume we know x is an element of. But we're going to say f increases for this interval, but that's not the only interval that he walks up. He's still walking up over here, but because of the discontinuity, we had to separate it into a new interval for which he is walking up. So he also walks up from negative 5 to 0. Now he starts to walk down for 0 to 5, and then again because of the discontinuity he walks down again from 5 to infinity. And if you would check with me that if we start going to the calculus part, every point on this curve would have a positive slope to tangent line, and every point on these two curves, two sections of the curve, would have a negative slope line. So this is pre-calculus. Look at a picture, tell me where it increases or decreases. Now we're going to calculus. So to use calculus, we're going to be looking at a function, and we're going to use calculus to determine where the function is increasing or decreasing. So what we're going to do is we're going to basically determine, we have a continuous function, so we're going to determine our critical values. So we're going to find the derivative, f prime of x, 3x squared minus 3x. Then because this is a polynomial, which would have no cusp or vertical tangents, all I know, and I'm continuous, and my domain is negative infinity to infinity, my critical values are only going to occur where the derivative is equal to 0. So the derivative equals 0 when x cubed minus 3 halves x squared equals 0. We'll do a little factoring here, x minus 3 halves, and so we would get x equal to 0 and x equal to 3 halves. So step 1 is find our critical values. And then what we're going to do is we're going to create a sign chart to organize our information, because what we know is that where our derivative is 0 is a place where it may switch increasing to decreasing. So we're going to put our 0 and our 3 halves. I'm going to label f prime of x as what I'm doing in my sign chart, and I'm going to label these as 0. Now if there were any discontinuities or any places where the derivative was undefined, I would add those on as well. Okay? Because those could be a place where you would switch increasing to decreasing as well. But I don't have any, so I don't have any to add. Then I'm simply going to test the derivative and determine its sign, positive or negative. Usually you do that, I can look at this and be like, hey, that's a cubic. The end behavior of a cubic with a positive lead coefficient is down and up on the ends. Okay. And if we test the value in between here, like 1, you're going to get a positive times a negative, which is negative. So we have a sign chart. Okay. Now, I like to put on my sign chart what f of x is doing so that I can kind of read off to myself. F of x is now decreasing, it's decreasing again, and then it's increasing. Now, a comment about sign charts. Sign charts are great organization tools for organizing the information so that you can answer the question. The sign chart itself is never the answer to the question in an FRQ. They will not look at this and say you've answered the question. What you must say in order to answer the question is f of x is increasing on the interval 3/2 to infinity because f prime of x was greater than 0. That's your answer with a justification, and your justification requires that you have calculus justification. Okay? You would answer the second part, f of x is decreasing on the intervals. What do we have? Now, the one comment that we'll make about this, we had a 0 right here. Now we want to kind of decide what's going on here at 0. It was a continuous function, okay, where as I was looking at it, it was decreasing, then it had a horizontal tangent, and then it was decreasing, and then it eventually increased again over here. So if we're looking at decreasing, would you say that this is decreasing the entire time? In this case, yes. You do need to evaluate, because I have a minus and a minus here, that this is not actually a place where I stop decreasing. It's not a discontinuity that's missing where I would need to eliminate it. It's not a vertical asymptote. There's nothing weird going on there. It just happens to be a place where as the slope was coming in, the slope itself reached 0, but the function itself was still decreasing. Okay. So it's decreasing, it's only on one interval. You want to be careful about that. Don't put 2 intervals. You want to say on the interval from negative infinity to 3/2. You want to think about what's happening here, not just blindly do 2 separate intervals on that. All right? And then the reason, because f prime of x is less than or equal to 0. And that's kind of why, in this one I did only greater than, because at this was a switching point. This was not a switching point. So it was decreasing and then decreasing some more. It just slowed down before it decreased a little bit more. All right, example 4. Again, open intervals where the function is increasing or decreasing. And again, we're using calculus. So we're going to find our critical values. Now we know that this is a continuous function and a differentiable function. So always important to keep in mind. We're going to take a look at our derivative, f prime of x, 12x cubed minus 12x squared minus 24x plus 0. We're going to say that our first critical values are going to occur when f prime of x equals 0. And that's going to occur when 12x cubed minus 12x squared minus 24x equals 0. Let's factor out our GCF. So I have x squared minus 1 x minus 2 equal to 0. 12x, let's see if this factors. 2 and 1, let's make this negative and that positive. So this happens at x equal to 0, 2, and negative 1. So we have 3 critical values where we have a slope of 0. And again, if I'm doing this, I should think about it. f prime of x is never undefined here. So then we create our sign chart to help organize our information. Sign chart is here purely for our information to keep straight what's going on. We add our critical values, -1, 0, and 2. The derivative is 0 at those locations. I then go through and I basically am going to do my test for my derivative. Where is it positive and negative? Again, I'm going to do the same thing I did before. I have a cubic with a positive lead coefficient, so it's going to be negative and plus on the ends. I'm trying to save you some time for testing. Maybe plugging in 1 would be easy. Positive, negative, positive. So overall, positive, negative is negative. Okay. Pick a number like -1/2, negative, negative, positive, so that's positive. Once I get what the derivative is doing, I then interpret it to what f of x is doing. Decreasing, increasing, decreasing, increasing. Okay. Then you will answer the question using calculus for your justification. The sign chart, again, is never accepted as an answer. It is your information, your organization, but you must answer the question. F of x is increasing on the intervals -1 to 0 and 2 to infinity because the derivative on that interval was greater than 0. F of x is decreasing on the intervals -infinity to -1 and 0 to 2, and our because is because the derivative was negative. So you are going to make sure that even if you have a sign chart here, that you answer the question and give a calculus justification. It's getting your full credit for these. Now let's go to the first derivative test. So now that we've done a nice review, let's do our first derivative test. Actually, I'm going to stop the video there and break this up into several videos.